science spectrum with Don. This is the 6th part of the 3rd lectures. And of course, we stopped from the 5th lecture. We were asked to find the area and the error limit in the area, given the length and the breadth, the measured values, and of course the error. So we've done that up to this point. So we proceed from there. So we have plus or minus the absolute error in the area divided by the value of the area itself, which we got from the product of the length times the breadth. And this is equals to plus or minus. Now we'll take the LCM. And of course the LCM would be the product of the denominators. So that is 10.2 times 9.4. Now when you divide the LCM by 10.2, 10.2 deletes out. So I'm left with 9.4 times 0.1. So I'm left with 9.4 times 0.1. Then I have a plus in between. The LCM divided by 9.4, 9.4 deletes out, and I'm left with 10.2, and that will multiply 0.2. So I have 10.2 multiplied by 0.2. Alright, so this is a plus or a minus 95.88 equals to plus or minus. Now, let's see what will come out from the top. So what I have here is 9.4 times 0.1, and this boils down to be 0.94. So this is 0.94, the product of the first two. Then I have plus 10.2 times 0.2, and of course let's check that properly. 10.2 multiplied by 0.2. This is 2.04. This is 2.05. And of course, when you multiply this, just like we had earlier on, this would translate to 95.88. And of course, this would boil down to be this pair of ratio. And of course, I could take the sum of this 0.94. I have 2.04. This is an 8, this is a 9. So this boils down to be 2.98 divided by 95.88. Now I have a pair of ratio on the left and a pair of ratio on the right. So if you look at the denominators on both sides, they're the same. So I could delete this out. So what I have left now is the absolute error in the area, which is plus or minus the absolute error in the area, which is the same as plus or minus 2.98. And of course, this would be in squared centimeter if we take the units along. So I could report the answer now as the area itself plus or minus the absolute error in the area. So the area itself, we figured that out to be 95.88. So this is the same as 95.88. That's the area. Then the absolute error in the area, that's 2.98, and of course they're all in squared centimeter. Alright, so this is the first question we'll solve. This is under errors in products. Now, you may need to beam this for a while. So, I will move on now to the next question, that is error in quotient, and lastly we'll talk about error in powers. Alright, so I take another example. Now this example would be, let's take for instance that we have to determine the time period of a simple pendulum. And of course the time period we have to determine that. However, for simple pendulum, the time period is given by this formula, 2 pi times the square root of root L over G. So let's say the length of the thread is, let's say, I will express it in terms of its percentage error. Let's say it's 1%, and of course, let's say G has an error of, let's say, 2%. Now, the question is this: we could find what the value of the time period is from the formula, but I'm quite interested in knowing what the fractional error in the time period is. This is fractional error in the time period. This is what I'm actually interested in. Now, I chose this question deliberately because this is actually, it deals with sum of errors that involves powers. Alright, so let's proceed. The solution to that is All right, so let's proceed. So solution. Now I do know that the time period of a simple pendulum, now 2 pi is just a constant, just a number. But I know this is the square root of L. This is the same as square root of L over square root of G. And the square root of L is L raised to power half. Now G is down. So G is carrying the square root sign. So it means the root sign, that's the power, would be a negative value. So this tells us now that I have 3 quantities that is related with this formula or by the formula. So clearly, to find the fractional or the relative error in the time period, this would be, now I have to, it will be the power, if you recall, the fractional error, the fractional error in x would be, that is when x is a raised to power n divided by b raised to power m. We figured out that this will be the power of n, that's the power of the first quantity, times the fractional, that's times the fractional error in this quantity. Then we'll stick in the plus. M, that's the power of the second quantity, times the fractional error in the second quantity. So we'll just apply the same thing to this. So this will be a half times the fractional error in L plus, now this has a minus, but I don't really need the minus sign. I only care about the value, just like we have the m here. So this is just also a half times the fractional error in G, which is called gravitational acceleration. Alright, so just a quick one. If I was interested in knowing what the time period is, I could just stick in the value, right? But since this is given as, if I was given the measured value, the measured value for G and the error, of course I could find the time period. But since this information is no longer here, or is not given in the question, so it simply means I could just find what the fractional error in the time period is. So we'll proceed from there. So the fractional error in the time period would be half, and this is just because this is just 1%, so this is just half times 1. I could throw out the percent plus half, and this is just a 2. This is just a 2, and of course I could stick in a plus or a minus there. Alright, so of course I could enclose this in a bracket. Alright, so what I have here is plus or minus, half times 1 is a half. The 2, I delete out the 2, so I just have, so this is half plus 1. So that is the fractional error in t. So plus or minus. So the fractional error in the time period would be half plus 1. This is half plus 1 over 1. Take the LCM. Or just multiply this term by 1. Multiply this by 1 over 1. Multiply this by 2. Both for the numerator and denominator, just to make the denominators the same. So this is 1 over 2 plus 2 over 2. So I have common denominator now. Then I could just sum what I have upstairs. That is 1 plus 2 over 2. This is 3.5. That's 1.5. So this is just 3.5, and that will give me 1.5. So the fractional error in the time period is 1.5%. Now we go to measurement of length. Look at the instruments for measuring length. Now you need to beam this for a while. I will wipe this up in a moment. And also that also. So measurement for length in the laboratory specifically. Now we measure length in the laboratory. Measurement of length. Or just called measuring instrument for length. The measuring instrument for length. Measuring instruments, right? And I'll start off with for the quantity length. Alright, so we measure length in the lab with a meter rule. A meter rule is used for measuring, let's take for example, dimensions of your desk, right? Or even your book. When you measure length that goes beyond the length of your desk or your book, of course, we could use the tape rule for that. Now, we measure length with the meter rule in the laboratory. The meter rule. This is for dimensions, length of your book, your desk. We could also measure with the tape rule. However, we could measure length of round objects. It could be their internal or their external diameters. So if we're trying to measuring the length of round objects, in this case now, it could be the diameter of round objects. We use the vernier caliper, or we could use the micrometer screw gauge. Now, the vernier caliper is used in measuring to an accuracy of a tenth of a millimeter or 100th of a centimeter. That is for the vernier caliper. That is what it measures, and it measures both the inner and the outer diameters of round objects, and it also measures the hollow, the depth of objects with a hollow. Therefore, the micrometer screw gauge, it measures only the outer diameters of round objects and also the thickness of very thin objects. Take for example, the thickness of a piece of paper. This could measure, a micrometer could measure that. The thickness for a wire, it could also measure that. Now this measures to an accuracy of 100th of a millimeter, and then also of 1,000. It measures to an accuracy of 1,000 of a centimeter. 1,000 of a centimeter. 1,000 of a centimeter. All right. In a subsequent bulletin, okay, let me also talk about the meter rule. Its accuracy is to 1 millimeter, but at times you could just divide this by 2. So we could say it is 1 millimeter or 0.5 millimeter. Of course, the same goes with the tape rule. Now, in a subsequent bulletin, I'll be detailed about these measuring instruments, that's the meter rule. I could skip for the tape rule, and I'll be detailed with the vernier caliper and also for the micrometer screw gauge. Thank you for tuning in. You want to like, share, and subscribe to this channel for more content. Thank you.